Hello friends, my name is Ajay Mulgir. Today I am going to discuss the examples on distributive lattice and modular lattice. Yesterday Sonal taught us about the distributive lattice and modular lattice. Today I am going to take example on this. First I will write the definition of distributive lattice and modular lattice, then we will proceed further.
You say it while writing.
Yes, A meet B join with A meet C is equal to A meet in bracket B join in bracket A meet C. And if another definition of modular lattice is if A is greater than or equal to C, then A meet B join C is equal to A meet B join with C. This is the definition of
Any one is all are equivalent statements. Distributive lattice, if one is satisfied, the other one is satisfied. Similarly, for modular lattice also we have two equivalent definitions for modular lattice, right?
yes.
Equal to.
Yesterday Sonal has taught us every distributive lattice is modular lattice, but converse of this lemma is not true. Today we will discuss the example that does not hold that every modular lattice is a distributive lattice.
Is not true.
Yes, is not true.
Right, little big. Handwriting दिख रही नहीं. हाँ.
The converse of this is not true. Let M3 be the diamond lattice, which is modular lattice but not distributive lattice, that we are going to prove. The diagram of M3 is
चाक पीस बराबर पकड़ो ना.
This is the diagram of diamond lattice. First we will show that this is a modular lattice. The definition of modular lattice is
It is there na? It is there. No need to write again.
A meet B join with A meet C, which is equal to A meet in bracket B join A meet C. We will show that the LHS of this is equal to RHS of this.
One second. So this is not only for this ABC. Actually, you take any three elements. For any three elements, this condition should be satisfied.
Yes.
Yes or no? That means first, A01, RB01, C01, or AB1. Any three elements you take, it should satisfy this condition, right?
First, we will take LHS of this. What is the A meet B? A meet B is 0. Join with A meet C. What is A meet C is 0, which is equal to 0. And RHS is what A meet as it is in bracket B join. What is A meet C? A meet C is 0. and at A, B join 0 is equal to B. And what is A meet B? A meet B is equal to 0. Hence LHS is equal to RHS. Hence diamond lattice is a modular lattice. Now
No,
we will.
is it clear? We have only checked for this ABC. Actually, there are other options one should verify. Are you following?
Yes.
It is not only for the 3 elements if you show. It is modular lattice means if you take any 3 elements from that lattice, it should satisfy that condition. For example, here you take A comma B comma 0. For those 3 elements also you have to show. Is that clear?
Yes.
But that you verify, it is not a problem. Okay.
Now we will show that it does not satisfy the distributive law. The distributive law is A join B meet C is equal to A join B meet with A join C. LHS of this is equal to A join B meet C is 0 and it is equal to A join 0. A join 0 is equal to A and RHS. What is A join B? A join B is equal to 1. Meet with A join C. A join C is 1, which is 1. Hence it is not equal to. Hence it does not satisfy the distributive law, but it satisfies the modular lattice. Hence it is the example of which is modular lattice but not distributive lattice. Now we will show that the pentagon lattice, that is N5, is neither modular or not distributive lattice. The diagram of the pentagon lattice is
चाक पीस बराबर पकड़ना है, साउंड ज्यादा कर रहे हैं, हाफ ले लो. Yes, it is for if any 3 distinct elements we have to. No, you take any 3 different elements, then it should satisfy. If you are taking 2 same elements, you are only checking for 2 elements, right?
It is a pentagon lattice. Now I will show that it is not distributive or it is not modular lattice. First we will show that it is not modular lattice. The condition for here we have to use the second one condition. Here A is in this definition A is greater than C and in here B is greater than A. Then we have to change that B meet C join A is less than or equal to B meet C join with A.
Equal to. We have to check whether it is equal or not.
Yes. Greater here B is greater than A, hence we can write this definition like this. Now we will check that it is equal to or not. LHS is equal to RHS or equal is not. What is C join A? C join A is 1. And what is B meet A? The B meet A is
B meet 1.
B meet 1, sorry. B meet 1 is B. And in RHS, what is B meet C? B meet C is 0. Join with A. Hence it is not equal. Hence we show that it is not modular lattice. Now
So you write there N5 is not modular.
Now we are going to discuss about the distributive law in N5.
Whether is it distributive?
No.
Why?
Today we are going to discuss.
Whether we need to check whether it is distributive. What we have proved?
Every distributive law is modular lattice, but converse is need not be true.
But we have proved that this n5 is not modular. So obviously it cannot be distributive also. Okay, because if at all it is distributive, it has to be modular.
Yes.
So we shown that it is not modular, therefore it is not distributive also, right?
Now we are going to discuss another example of distributive lattice. Now today I am going to discuss another example of distributive lattice.
ऑडियंस को देखना है, कैमरा को नहीं, है ना?
Yes.
हाँ। हाँ ना, suppose if you take any distributive lattice, so take an example of distributive lattice, then obviously it is distributive as well as it is modular.
That I am going to take.
Is that clear? So we have seen so far something is modular but not distributive, and we also seen neither modular nor distributive.
Let n be a set of natural number, and we define for a comma b belongs to n, we define meet and join of these two elements is a meet b is equal to GCD of a comma b, and a join b is equal to LCM of a comma b. Then we have to show that it is a distributive lattice under meet and join. We have to show that this is distributive
Right, there
lattice.
is distributive claim.
If we prove this is distributive, then obviously it is modular lattice by using the lemma. The condition for the distributive lattice is A join. We can use any one of them. A join B meet C is equal to A join B meet with A join C.
That we want to show. You write
This we have to show that this is
you
our
write
claim.
as that is.
In this, first we will take L left hand side, and then we will go for right hand side. Take any three elements in natural number 2, 4 and 6.
Now why you are taking example?
It is example.
No, if at all we want to show it is distributive, we have to prove it for any three numbers, right?
Yes.
If it is not, then you can take example. Yes. For understanding you can take, right? Explain what you are explaining.
तर ते GCD वगैरे काढताना आपल्याला एक्झाम्पलच म्हणजे कोणते बी नंबर घ्यावे लागतील. एनी नंबर वी कॅन चूज इन नॅचरल नंबर.
नहीं, लेकिन while proving you have to prove for general only, not for any particular numbers, right?
Yes.
Okay, you explain first what you are prepared.
Yes. Suppose we choose A is equal to 2, B is equal to 4 and C is equal to 6. Then we verify that the LHS is equal to RHS. First we will go for LHS, then we will go for RHS. What is A? 2 join 4 meet 6. But what is the meet operation here? Meet is GCD. GCD of these two elements is 2. 2 join 2 is equal to 2. Now we will go for right hand side. What is the right hand side? 2 join 4 meet with 2 join 6. What is the LCM of these two? It is 4. what is the GCD of these two? So, hence we prove LHS is equal to RHS.
This is only true for a particular 3, right? So even if you prove for 1000 numbers, but
Yes.
it may be possible that for there are 3 numbers it is not true. Okay, so are you following? So this is not the proof, it is only for understanding. But when we want to prove that it is true, what are we are supposed to do? Right? A join B meet C, right there, that's it.
A join B meet C.
Right there. There. No, don't rub. You write there, you have space now, that's it. A join B meet C equal to is equal to what is, first of all, it is join of 2 elements. So it is, what is join? LCM, right? LCM of A comma then B meet C. It is same as, right, next step equal to LCM of A comma what is B meet of 2 elements is GCD of A comma B. And what is the other side? A join B, right hand side, well, A join B meet A join C. There you write B comma C.
A join C.
Upar. One second. Above B meet C, na? So GCD of B comma C.
Here GCD of what is A join B? A join B is LCM.
No, first it is meet, na? It is meet. See, it is meet of 2 elements.
Yes.
So first write GCD.
Yes. GCD. GCD of
A join B comma A join C. Next,
Then
you write equal to GCD of
what is A join B?
LCM of A comma B.
And LCM of A comma C.
So now you have to show these two are equal for any natural number ABC.
Yes.
So this you try, and if you are not getting, I will explain nextly. Is this clear? This is only for understanding. That take 2-3 numbers, then you verify. But you are supposed to prove LCM of A and GCD of B comma C is same as GCD of LCM of A comma B and LCM of A comma C.
Yes. Similar type of another, we can take another example.
You know what is meant by, just a second, you know what is meant by GCD, right? Suppose you write that as some X or whatever R. So it satisfies, it is the greatest common divisor. And you know what is meant by LCM. Okay. So show that those two are equal. Everyone
Yes.
try that.
Let n be a natural number, set of natural number, and let small n be any number in natural number. Then A meet B is GCD of A comma B and A join B is LCM of A comma B. Then we have to show that n is a lattice where n is a positive divisors in lattice. Then we have to show that L is lattice and we have to choose the positive divisors of n under positive divisors of n. If we choose n is equal to 50, then positive divisors of 50 are 1, 2, 5, 10, 25. Then we can choose any 3 element and we can show that it is a distributive lattice. Choose any 3 elements. We will choose these 3 elements. A join B meet C is equal to A join B meet with A join C. we choose this is A, B and C. Then we have to show that LHS is equal to RHS. First we go for left hand side. What is A? 2 join 5 meet 10. What is the GCD of 5 comma 10? What is the LCM of these two? In RHS, what is the 2 join 5? Meet with 2 join 10. What is the LCM of these two? 10. Hence, we verify that LHS is equal to RHS. Hence, this is another example of distributive lattice as well as modular lattice.
Here also he has explained only for one
Particular case.
but because it is finite, you have only 6 elements, right?
Yes.
So you can have different permutations and you can check. But the first one, if at all you have to prove it for
General case.
But see, suppose if you prove first one for any n natural numbers, if it is true, then these are all obviously subsets of that one, right? If for any 3 natural numbers, if it is true, then if you take even in particular divisors or if you take prime numbers, obviously it will be true, right? Yes or no? If at all, if you can prove that it is true for any 3 natural numbers, then obviously when you take prime numbers also it is true. If you prove for any 3 prime natural numbers, if it is true, then prime numbers are also part of natural numbers, na?
Yes.
What I am saying, suppose you are proving globally, if at all you prove that for A, B, C, any natural numbers, if this is true, then obviously prime numbers or whatever even integers you take, they are all subsets of that, na? If you prove it, suppose you prove for something is true for prime numbers, then you may not give guarantee that it is true for all natural numbers. But once you prove that it is true for bigger collection, then obviously if you take any subset, it is also true or not? Huh?
Now we will discuss definition of bounded lattice. Let L be a lattice and 0, 1 belongs to L, then 0 is less than x is less than 1 for all x belongs to L. In this definition, we can choose any element of lattice which must lie between 0 and 1, then we can say that it is a bounded lattice.
Here 0 and 1 means 0 is the
Endpoint.
minimum element and 1 is the maximum element. Okay.
Now we will discuss the definition of complement. In set theory, we have discussed that the complement of 2 elements like this, if this is diagram, this is A and B and this is whole set X, then what is the A join B? A join B is whole X and A intersection B is equal to 0.
Empty set.
Yes, 5, sorry. 5. Similarly, the definition of complement lattice is if A is complement of B, where A comma B belongs to lattice L, then we can write as A mid B is equal to 0 and A join B is equal to 1.
No, this is the definition, not then. A is complement of B if, you write there if. You erase there A comma B belongs to L. You start with
Yes.
A comma B in L. We say that A is complement of B if it satisfies this
These two
condition.
conditions, yes.
Obviously, B is also complement of A or not, because meet and join you can interchange. Yes or no? So basically, if you take the meet, it should be the minimum one, and if you take the joint, you should get the whole maximum element. Is that clear? Then we say that one is complement the other.
Yes. Now we will discuss the lemma. The statement of the lemma is, in a bounded distributive lattice, there is at most one complement.
You draw one second. Before that, you draw their picture. That diamond lattice.
Diamond is not distributive.
No. You write there.
Yes.
First, you draw that picture.
M3. This is the diamond lattice.
Now, what are the elements? Can you give one or two elements which are complement to each other? Wait. First, you discuss that.
Yes,
one.
yes.
Huh? What can you say about suppose A and B? Whether A is complement to B? A is complement of B or not? Because if you take A and B, their meet is 0 and their join is 1. Okay. Suppose if you take A and 1, whether A is complement of 1? Whether A is complement of 1? No, right? Now we said right there A is a complement of B. Yes or no? A is a complement of B. And right now, otherwise they will understand C, B. A is complement of B. Now what can you say about A is a complement of C or not? Why? Because if you take their meet, it is 0 again, and you take the join, it is 1. So A is also complement of C. Is that clear? That means for this A, you have two complements, B and C. Are you following? Yes, you write there. A is complement of C also. Yeah, there is nothing about A, B, C. That means here in this example, we are seeing that one element can have more than two complements. Are you following? Yes. It is a notation. We have mentioned in that notes also, 0 we will consider as the least element in that lattice, and 1 is nothing but the maximal element. Okay. When you define bounded lattice, there 0 and 1 it is written. That means 0 is the notation. Whenever we see 0 and 1, it is understood that 0 is the smallest element in that lattice and 1 is the largest element in that lattice. Okay.
Now we will discuss the lemma. The statement of the lemma is, in a bounded distributive lattice,
So why I given that example? Because don't go just simply by writing we will prove this lemma, then we go to this one and so on. It is understood. You have to understand that there are some lattices where one element can have more than one complement. Is that clear? An element can have more than one complement, and that is one example. But once we have a bounded and distributive lattice, this example it is bounded, but it is not distributive. Okay. So whenever we have a bounded and distributive lattice, that doesn't arise. That means any element, if at all it has a complement, there will be only one complement. Are you following? Here we are not saying that every element will have a complement, one complement. There will be at most one complement. Okay, some elements may not have any complement. This statement is not saying that every element will have a complement. Are you following? If at all there is any complement, then that will be unique. Is this clear?
Now we will suppose that there exist two complement of one element, then we will show that these two are equal. Suppose that A comma B be the then we have to then our claim is A is equal to B. For that we have to show that A is less than or equal to B, or B is less than or equal to and B is less than or equal to A.
Not implies, that is I dot E.
Yes. First we have suppose that A comma B is a complement of C. Then by using the definition of complement, we can write as A meet C.
बड़ा राइट लिखो. हाँ.
A meet C is equal to 0 and A join C is equal to 1, whereas B meet C is equal to 0 and B join C is equal to 1. But we can write as B is, or first we will show that B is less than or equal to A. That is B meet A is equal to B. That we have to prove. For that we suppose that B is equal to B meet 1. This we can write. B is equal to B meet 1. And instead of 1, we can write as A join C. Hence it is a distributive lattice, hence we can separate the bracket also. B meet A join with B meet C. What we have to show that B meet A is equal to B. B meet A. What is a B meet C? Here B meet C is 0. But join of these two is B meet A. Hence we prove that B is equal to B meet A. That is B is less than or equal to A. Similarly, we can prove that A is less than or equal to B.
That you can skip, right? Yes or no? A less than or equal to B.
Hence we prove that in bounded distributive lattice there will be at most one complement. In diamond lattice there has more than one complement, hence it is not distributive. We can skip the definition of distributive lattice. Using this lemma, we can easily check that whether the given lattice is distributive lattice or not.
That means what is trying to say is this lemma we can use to show that something is not distributive. Yes or no? If we have a bounded lattice and one element has more than two complement, then obviously it cannot be distributive. Is this clear?
Now we will discuss the definition of complement lattice. This is the definition of complement. Now we will discuss the definition of complement lattice.
No.
A bounded lattice is said to be complement lattice. A bounded lattice is said to be complement lattice if every element has complement. That is M3 and N5 is complement lattice.
One second. See, first of all, when we discuss about complement, what we require is that lattice should have 0 and 1. Is this clear? Yes. Because when you talk about meet and join, it should be 0 and 1, right? So, not only that, if 0 and 1 are not there, you cannot discuss about complement or complement lattice. Okay. So, whenever we say complement lattice, first of all, it should be bounded. That means it should have 0 and 1 and every element should be, once you say 0 and 1, that means it is bounded or not? 0 and 1 means 0 is minimum and 1 is maximum. So, every element is in between that. Are you following?
Now we will.
And what are these? These are the examples, right? Just their examples. We have seen today M3 and N5, right? Okay. Here we have seen M3.
I draw a diagram of N5.
Okay, first at least try to understand for M3. You can see that every element will have at least one complement there. Are you following? We have seen already for A, B, C, right? And for 0, what is the complement of 0? What is the complement of 0? 1, right? Yes or no?
Now I will.
Huh? A meet? No, but that you can do it, but what you require? Whether that element is complement itself or not.
In that definition, there must be lattice, every element has element, every existing element present.
Every element has a complement. Say suppose you take A. Distinct, when you say distinct, when you are talking about two elements. Every element should have a complement. For example, in M3, how many elements are there in M3? 5 elements are there. So, all 5 elements should have a complement. Are you following? Some complement, same it may be. You know, it require that every element should have a different complement. Okay. So, here for example, A and B if you take. For A, what is complement? B is also complement, C is also complement. Yes or no? But definitely A has a complement. Similarly, if you take B, A and C are complements. For C, A and B are complements. For 0, 1 is the complement. Yes or no? Right? So, if every element has complement, then we say it is a complement lattice.
Now we will discuss the De Morgan's law for distributive and modular lattice.
N5, can you draw N5 here?
Yes.
This side? So, for a complement lattice, you don't require that it should be distributive or it should be modular like that. Is that clear? For this, what is complement of A? What is complement of A? C. Yes or no? What is complement of B? Is again C. Yes or no? For example, what is complement of C? Is either A or B, right? Then complement of 0 is 1, right? So, here also you will see that one element has more than 2 complements. Yes or no? Okay, so this also is not distributive. Are you following? Okay, so these 2 examples are not distributive lattice, follows from the previous lemma which we have proved, right? Once 0 is complement of 1, then 1 complement is 0, right? If A is complement of B, then obviously B is also complement of A.
Now we will discuss the De Morgan's law.
बड़ा लिखो ना, आप इतना हाइट है। हाँ हाँ
let A and B, let A and B let A and B have complement. A dash and B dash,
complements. हाँ
A dash and B dash. Then we have to show that A meet B, comma A join B have complement. Have complement A meet B dash and A join B dash. That we have to prove what is in statement that is given that A meet B dash is equal to A dash join B dash, whereas A join B dash is equal to A dash meet B dash.
one second. After that, let A and B have complements. We have denoted that as A prime B prime, right? Write full stop. Then you write after that, not there. After that, full stop. Then see, whenever A and B have complements, then their meet and join also have complements. Obviously, what are those complements?
A meet B dash.
If you want complement of A meet B, then you take the complement of A and complement of B and take their join. Okay, is that clear? So it is just like De Morgan law.
This is true in bounded distributive lattice. Bounded distributive lattice. This is true in bounded distributive lattice. Now we will go for proof of this De Morgan's law. What is given that A and B have complement A dash and B dash. By using the definition of complement, we can write as A has complement A dash, which is equal to 0, and A join A dash is equal to 1, whereas B has complement B dash. B meet B dash is equal to 0 and B join B dash is equal to 1. And what is our claim? Our claim is that A join A meet B is equal to A meet B dash, that is equal to A dash join B dash. If we prove for this, then we can obviously say that this is same for join also.
You write their claim that we are supposed to prove.
Yes.
A meet B prime, we want to prove it as A prime join B prime, which is the complement of A meet B. Is that clear?
We have to show that this is complement of this, that is A meet B. A meet B, complement means meet of A meet B dash is equal to 0, or A meet B join of A meet B dash is equal to 1.
And not R, and both you have to.
Yes, and also we can show for this.
Similarly, you can show for join also.
Join also.
No need to write that. First you.
Oh, here is join and here meet. Yes. Yes.
See, A meet B.
First we will show this.
1 second. We are going to prove that complement of A meet B is A complement join B complement. Yes or no? A meet B prime is A prime join B prime, right? So we will substitute that and we will take the meet with A meet B and see whether you get 0 or not. Are you following?
Yes.
So you take A prime join B prime, show that it is the actually complement of A meet B. Is that clear?
First we will show the first one, then we will proceed for second. What is first? A meet B. We can distribute this, we can write this as A meet B meet with, what is this? A dash join B dash.
No, we have to prove that. Okay, we will show that. So we will take this value. Are you
We
following?
have to show that this is equal to
We will
0.
show that we will take this A prime join B prime and we will meet with A meet B and show that it is 0.
Yes.
You calculate that. What is that value?
Yes. We can separate this since our lattice is bounded and distributive. So let's separate this term.
But how you will separate this?
Let call this as x, then we can separate this
Okay.
as x meet A dash, x
Join
meet A dash
bracket.
meet with x meet B dash.
Join, na? There in between join.
Here is
X meet A. X meet A dash join. Join.
either
Those join. What is X meet A join
Yes,
C? Is
yes.
X meet A join with X meet C?
join with x meet B. We substitute the value of x. What is the value of x is A meet B. A meet B meet with A dash and join with A meet B meet with B dash. What is the value of A meet A dash? A meet A dash is 0. Which we can write as B meet 0. And here, what is the value of B meet B dash? 0. Hence A meet 0. What is the meet of this is 0, join 0 is equal to 0. Hence we prove first property. Now we will proceed for second. What is the second property? A meet B, A meet B,
Join.
join with, we can separate this dash as A
You take
dash,
again A prime join B prime.
A prime join B prime. This we have to prove is equal to 0.
One.
This is our claim.
It is 1, na? You want to prove it is
Sorry,
1.
1. This we have to prove. Similarly, we can separate this also by using the distributive law. Hence, it is distributive lattice. Hence, we can use the distributive law. We can separate this. Call it is a x and x join A dash join with x.
In between you get meter.
Correct. I will substitute the value of A meet B. What is the value of A join A dash?
You write properly.
Yes,
There
yes.
is a 1 sec. There is a bracket, na? You have a bracket there. Huh?
Sorry. Here we have to separate this. Again, we can separate this. A dash join A meet with A dash join with B. B dash join with A meet with B dash, join with B.
आपको वॉइस वहां तक नहीं आ रही है,
Yes.
बोलना जोर से। हाँ?
ठीक है सर।
हाँ, आपका आप बता के लिखते जा रहे हैं।
What
नहीं
is
तो पीछे
A?
लोग सोएंगे ऐसा है तो। हाँ?
What is A? Join A dash join A. The A dash join A is equal to 1. 1 meet A dash join B. And similarly for this, what is B join B dash is equal to 1. But we can, what is this? A dash join. Hence, this we can write as
From there, what? How you will get this? Huh?
something went wrong. X join A dash.
Huh?
Here we suppose this is as X, then X join A dash is X join A dash, hence it is join B dash.
So nobody has noticed that there we are not supposed to apply distributive.
Yes.
Huh? That means you are not actually following. Huh? It is actually join of 3 elements, not actually distributive. Distributive means it should be join and meet. Yes or no? Huh? You are not. You might have not erased that. You go back and see that that is not actually distributive. But everybody is saying distributive, so you simply simplify. Are you following? And then how you will simplify this after that? Huh?
X is what? A meet B, join with A dash, join B dash. Yes, now we can use the distributive law. What is the distributive law? Here is A dash join A meet with A dash join B.
Huh? No, no, वही prove कर रहे हैं ना. That only we are proving. No, 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 we are supposed to prove that. हाँ.
What is A dash join A? 1. Here is 1 meet. What is
Now what is this one? When you meet with one, you get that.
yes. Yes, it is join. By these two we can,
It is 1.
it is 1.
A prime
A
join
dash
1.
join 1 which is equal to 1. Hence we prove second one also. This is for my lecture. Thank you.
Good.